In order to establish the army, Liu Bei had encountered several expenses, so he asked Zhang Fei to determine how much money had been spent so far. Zhang Fei set to work using counting rods for his calculations. However, just as he was close to finishing up, and to his great surprise, a cat jumped through the window and messed up his rods. This left part of his calculation unknown. Zhang Fei knew how many rods were involved in the calculation, yet he had no idea how to recover his work. This calculation was important for future reference, so the confused Zhang Fei told Liu Bei about the accident. Liu Bei then took out his magical tablet to see if it could help them to recover the calculation.
So Zhang Fei is in charge of accounting for the army, and he's sitting there doing his accounting when a cat jumps in and messes up the figures. Now, the point is he's doing accounting using a system of counting rods, and after he sees the cat bounces around, he can see that 12 rods have been knocked off the table and not in their position. And he remembers that all of the digits in these positions were different. So basically he has to solve a problem of working out what were the digits that have gone missing, that the cat has mixed up. So just a briefly word about counting rod representation. So this is a way of representing digits using up to 5 counting rods, and there's 2 different ways, vertical and horizontal. And in fact, that's a very neat trick where you can keep vertical and horizontal alternating so you can leave out digits by doing that, although we won't use that in this example here. So he's got, here is the representation of what those counting rod digits actually meant. So here was in Arabic numerals, basically the arithmetic that's going on here. And of course, this arithmetic should hold. So that's another part of the problem. So let's look at building a model for that problem. So what do we have? We have a set of digits from 1 to 9, and then we've got this array of how many rods it takes to represent each digit. So the digit 1 is only 1, and 2, and 3, and 4, and 5 for representing the digits 1 to 5. But then you need 2 digits to represent 6 and 3 for 7, 4 for 8, and 5 for 9. You can look back. If we look here, the number of representations for 6 is 2, and 3, and 4, and 5. Okay, so that's basically telling us how many rods we require to represent each digit. And then we have 5 different things we need to know, basically each of the 5 messed up digits. So if we look back at the example here, we have 1, 2, 3, 4, 5 messed up digit positions. And then we've got our constraint. Well, we know the number of rods in the digits that are messed up sum up to 12. Okay, and then we're trying to make sure that the constraint holds. So if we take the first number, it would be 2003 times M1 times 10, because M1, that's this missing digit here, fits in the 10 digits position. So it's going to give us the value of the first expression. Then we take the second expression, which is 980 plus M2 times 1000 plus M3, because here's M2, that's in the thousands position, and M3 is in the ones position. So that'll give us the sum of the top 2 numbers, and then we have to add up to get the right value underneath, which is 301, which is the digits are given, times M4 times 1000, because the M4 is in the thousands position, and M5 times 10, because it's in the tenths position. But one thing we should note here is we are looking up using a decision variable into an array. All right, so this is a very powerful modeling ability of things like minizinc. We can use a variable here. We're going to look up using the digits here, which is a decision, how many rods it takes for that decision. Now, we've got to continue. We know that each of the 5 missing digits are all different. We could write down all of these not equal constraints to make sure that all 5 of those digits are different. So that's tedious, it's long, it's also prone to error, you can leave off one. So let's do it a different way. The way we're going to do this is by introducing an all different constraint. So this is an example of a global constraint, which is what we're going to talk about a lot in this course. So here's the all different constraint saying everything in this list of digits, M1 to M5, has to be different. So it's just a shorthand way of writing down all of this information in one go. But its definition is in a different file, so we have this include statement here, which says we've got to include the definition of the constraint, all different. And that's in this alldifferent.mzn file. And then here's our global constraint, the use of the all different. And since the problem is just to find a solution, we're just running solve satisfy to find what is the solution for these variables. There's nothing to optimize here. So we've seen a few new things in this model. So we had a set of type. So here, rather than use a numerator type, we used the digits from 1 to 9. So here was we gave a name to that. We called digit this name from 1 to 9. Right? So this can be used in place of any fixed set. So that's often what we'll do also is build ranges and give them names and use those just like we used enumerator types. We also have variable lookups, as I said here. We can use decision variables as part of an index expression, and this is going to give us a very powerful modeling capability which isn't in many other modeling languages. So here we're using it very, very simply. Basically, for each missing digit, we're using this array lookup to look up how many rods it took to represent that digit. We'll see many more examples of this later on. So we also saw an include statement here. So include just has include and then a file name. That's all you need for the include statement. And basically it takes the contents of this file and just imports them directly into your minizinc model. And it'll look in the current directory. So you can use it to break a model into parts, or it'll look in the minizinc library path, which is what we're doing here, is looking up, finding the definition of all different and including it in our model. So include statements allow us to break larger models into small pieces, although we won't do so much of that during this course, but when you're building large real-world models, it's very useful. It allows you to load library definitions of global constraints, and that's what we're doing here. We're loading a library definition of the all different constraint into our model. And the nice thing about this is this global constraint definition we load will be different depending on which solver you choose to use. And this is one of the key things that global constraints allow us to do, is allows us to give a version of the constraint which is specialized for the particular solver we're going to use for running the model. So even though we write the model with one all different, different solvers may see a different way of representing that all different. Okay, and global constraints. So technically a global constraint is any constraint which has an unbounded number of variables as input. And so we've already seen linear constraints, like some expressions are kind of global constraints. But here, global constraints typically will be a name of the special constraint and then some arguments, usually with arrays because they're taking an unbounded number of variables. So global constraints are used to store constraints that arise in many problems. And using the global constraint makes the model smaller. You can see here, once we used all different, we made a much smaller model. And it does more than that, it makes solving easier. So typically, here we pass the all different constraint to the solver. The solver will know specially how to solve that constraint. So basically we are recognizing some structure of the problem, which occurs commonly in many problems, and passing that information to the solver, and then that solver can use that information to solve the problem more effectively. So if we run our model, we're going to get out an answer here. You can see each of the digits is different, and if we count the number of rods in these blue missing digits, you'll see they add up to 12. So we've got a solution to our problem. So in summary, we've introduced global constraints. That's one of the most powerful concepts we'll see in this course. It's a way of recognizing and naming combinatorial substructure, which occurs frequently in many problems, and giving that information to the solver to be able to allow it to do the best job it can on that particular combinatorial substructure. Another powerful modeling approach we've seen here is the ability to use a decision variable as an index into an array expression. And this will allow us to build very, very complex constraints by building up arrays and using decisions to look into those arrays to find the appropriate part that we need for the model. So here we're just using a very simple example, but we'll see much more complicated uses of this later on.